Buenos días a todos. Good morning, everyone. Bueno, estamos muy emocionados. Les damos la bienvenida al primer simposio mexicano de Radioterapia FLASH. Es un evento muy importante, tanto para el Instituto Nacional de Neurología y Neurocirugía, como para toda la radioterapia en México y América Latina. La radioterapia FLASH es una técnica de vanguardia. Es un hot topic ahorita en estos momentos. Están ensayos preclínicos y seguramente lo vamos a ver en el futuro. Welcome, everybody, to the first Mexican Symposium on FLASH Radiotherapy. Y este es un simposio que se va a dar en español y hay servicio de traducción para los que necesiten. Está afuera todos los dispositivos que requieran. Muy bien. Vamos a presentar la mesa del Presidium. En primer lugar, es un honor presentar al doctor Benjamín Pinedo Olvera, nuestro director de investigación. Al doctor Ramiro Gilberto Ruiz, en representación de la Dirección de Enseñanza, de la doctora Fabiola. A la doctora Onis Garay Villar, presidenta del Consejo Mexicano de Certificación en Radioterapia. A la doctora Mariana Hernández Bojorges, vicepresidenta de la Sociedad Mexicana de Física en Medicina. Al doctor Guillermo Axayacat Gutiérrez Aceves, jefe de la Unidad de Radiocirugía de nuestro instituto. Y finalmente a la doctora Paola Ballesteros Cebadura, investigadora en Ciencias Médicas del Laboratorio de Física Médica de nuestra institución. Bueno, a continuación le cedo la palabra a la doctora Ballesteros.
Pues muy bienvenidos sean todos a este simposio de Radioterapia FLASH. Es para mí un gusto tenerlos aquí. A todos los presentes, también a los que están conectados vía virtual, que son de toda Latinoamérica. Bienvenidos a los que se conectan desde Colombia, de Bolivia, de Brasil, de Venezuela, de toda Latinoamérica que nos están escuchando vía virtual, y también a todos los presentes, que algunos vienen desde diferentes partes de la República. Gracias por estar aquí. Quiero agradecer principalmente a las autoridades del instituto por todo el apoyo brindado, al departamento de enseñanza, a todas las facilidades del departamento del auditorio, el departamento de comunicación social y a todos los voluntarios que están participando para que este evento se lleve a cabo. También necesito agradecer a todas las sociedades cuyos representantes nos acompañan y que nos dieron el aval para la realización de este evento. Gracias en verdad por su apoyo. Gracias también a nuestros patrocinadores, porque sin ellos pues este evento no sería posible. Gracias a Extral, a Suma, a Blue Physics, a IMSA y sobre todo a la Swiss National Science Foundation, que ha patrocinado este evento. Yo quisiera compartirles que en septiembre del 2018 fui a una reunión y tomé una foto que no sé si puedan transmitir. Y esta foto fue en el Radiation Research Meeting, y fue la primera vez que escuché sobre la radioterapia FLASH. Y fue una experiencia para mí pues muy enriquecedora, porque yo nunca había oído hablar de qué era, y recuerdo haber dicho, wow, es algo increíble, ¿no? Porque rompe paradigmas que existen actualmente, y sobre todo porque pone muchas preguntas en radiobiología, en física médica, en radioterapia, además de ofrecer una alternativa para tratamientos. Entonces, ese día, pues para mí fue una experiencia muy enriquecedora, y bueno, yo no sabía que años más tarde iba a tener la oportunidad de colaborar con la doctora Bozenan en un proyecto de investigación justamente sobre radioterapia FLASH. Entonces, bueno, justamente la idea es que la radioterapia FLASH es una promesa y es una tecnología que está todavía en desarrollo, pero queremos que Latinoamérica y que México no se quede atrás en los desarrollos de vanguardia, y es por eso que están todos ustedes invitados. Este es un simposio interdisciplinario, en donde vamos a tocar áreas como la radiobiología, la radioquímica, la física médica, y es un simposio pionero. ¿Por qué? Porque vamos a tener a la doctora Bozenan, que es precisamente quien redescubrió la radioterapia FLASH, y es la pionera de esta área y que ha impulsado el crecimiento de esta área. Vamos a tener al doctor Limolli, que él es el pionero en investigar los efectos de la radioterapia FLASH en el cerebro. Vamos a tener a la doctora Tsutsu, quien es pionera en desarrollar un programa translacional a pacientes en Suiza de la radioterapia FLASH. Vamos a tener al doctor Franco, que es pionero en el desarrollo de un modelo ortotópico pediátrico de meduloblastoma para probar la radioterapia FLASH. Y vamos a tener a Marcos Feijó, que es pionero en dosimetría y en transformar equipos convencionales de radioterapia a radioterapia FLASH. Entonces, bueno, pues incluso nuestros patrocinadores nos van a estar compartiendo tecnología pionera en esta área. Entonces, por lo tanto, pues espero que este simposio, como lo fue para mí esa primera plática, y si algunos de ustedes es la primera vez que escuchan sobre la radioterapia FLASH, pues espero que sea una gran experiencia. Bienvenidos a todos. Les quiero recordar a los que quieran su constancia que les necesitan firmar el registro a la entrada. No se les olvide. Muchas gracias.
Muchísimas gracias, doctora Paola. ¿A alguien del presidium le gustaría dar unas palabras, por favor? Doctora Onyx.
Hola, pues muy buen día a todos. Trataré de ser lo más breve posible porque sé que tenemos una jornada larga, pero muy interesante. Agradezco de verdad a los organizadores, ¿sale? Porque es muy importante que nos hayan tomado en cuenta como Consejo de Certificación en Radioterapia. Siempre lo he dicho, somos sociedades hermanas, entonces colaboramos y trabajamos para el bien pues, de nuestros pacientes, ¿no? Que para eso es a lo que nos atañe. Entonces, parte de lo que pedí dar estas palabras es porque este mismo trabajo colaborativo que se realiza entre las sociedades y la importancia de la física médica, de los radiooncólogos, de todos los que forman parte de lo que es el grupo que trabajamos para dar tratamientos con radioterapia, consideré importante como presidenta tomar en cuenta esto que realizan día a día los físicos, porque pues, sin ustedes no sería factible, ¿no? Que los tratamientos estuvieran otorgados de adecuada manera y con la mejor calidad para los pacientes. Entonces, me tomé el atrevimiento, así lo quiero mencionar, de pues, mandar una carta a CONASEM. CONASEM es el consejo donde se certifican todas las especialidades médicas y entonces siempre nos dicen que si nosotros contamos con alguien más que queremos certificar, pues obviamente lo propongamos. Entonces, por parte del Consejo de Certificación en Radioterapia, se mandó la carta, entonces, donde nosotros propusimos que por parte de la colaboración que tenemos con Física Médica, consideramos importante que se certificaran a los físicos médicos que otorgan tratamiento con radioterapia. Entonces, es una propuesta que se realizó, quería comentárselos, para nosotros creo que es muy importante. En este bienio, pues obviamente me di la tarea de que los físicos participaran más activamente. De hecho, ya evaluaron a los radiooncólogos, de verdad fue algo muy importante, porque no nada más los radiooncólogos somos los únicos que tenemos que ser certificados, también los físicos tienen que certificarnos a nosotros que contamos con lo mínimo indispensable para poder otorgar los mejores tratamientos. Entonces, de verdad fue algo muy bueno que se realizó. Los recién certificados pues estuvieron muy a gusto, de hecho dijeron que qué bueno que se estaba ya implementando este tipo de acciones. Entonces, pues bueno, se los dejo a ustedes, piénsenlo, pueden emitir sus palabras, ya posteriormente la doctora Paola y todos los que están aquí, los formadores de físicos médicos, pueden ya contemplarlo, pero sí, es algo que se los quería comentar. Entonces, para que ustedes mismos puedan ser certificados por ustedes mismos, por un board especialista en esto y puedan tener un certificado. Este certificado dura 5 años. Entonces, pues bueno, yo les agradezco a todos realmente el estar aquí, el que se haga esto, para pues obviamente que esto sea trascendental, ¿no? Que finalmente tenemos que ver hacia el futuro y pues sabemos que los avances tecnológicos están más allá de todo lo que nosotros nos queramos resistir. Creo que tenemos que estar ahí, al igual que la inteligencia artificial, o sea, todo suma. Entonces, pues bueno, yo creo que esto va a ser de un gran éxito y nuevamente gracias por la invitación.
¿Algunas palabras del presidium? Adelante, doctora Mariana Hernández.
Gracias, doctor Larraga. Gracias, doctora Ballesteros, por la invitación, por la consideración a través de la Sociedad Mexicana de Físicos en Medicina. Yo soy Mariana Hernández y solamente quisiera aprovechar la oportunidad primero para agradecer la consideración a la inclusión, a la representación de la Sociedad Mexicana de Físicos en Medicina, que como la mayoría de ustedes saben, me imagino como físicos, especialistas en física y matemáticas, con una aplicación en el área de la salud, pues somos como un ente un poco más extraño de lo que regularmente pueden ser los físicos. Entonces, en efecto, nos ha costado mucho trabajo posicionarnos con el reconocimiento social, incluso profesional, dentro de nuestros propios compañeros de flujos de trabajo, médicos, técnicos, radiólogos, radioterapeutas, enfermería, anestesia, como profesionales insertados en la aplicación en un área de la salud. Ciertamente, y aplaudo y agradezco las palabras de la doctora, porque la búsqueda de un mecanismo de certificación que requiera y que garantice que como físicos con un desempeño en el área de la salud tenemos los mínimos requisitos para poder estar desempeñando esas actividades, es una de las etapas que estamos muy interesados como Sociedad Mexicana de Físicos en Medicina, representantes de las, parte de las representantes de los físicos que de manera primaria están enfocados al área clínica. Nos encantaría, doctora, poder enlazar y generar estos mecanismos que ciertamente en el país estamos todavía faltos de ello. Entonces, por favor, tómenos la palabra, tómenos en cuenta y podemos trabajar para cristalizar esto, que es una gran necesidad. Y también quiero decir que estoy altamente emocionada por estar aquí. Esta es mi casa de origen, el Instituto Nacional de Neurología y Neurocirugía es mi casa de origen profesional. Estoy muy emocionada, muy contenta de ver cómo ha crecido toda la física en medicina. Me tocó llegar aquí con el doctor Lárraga y la doctora Amanda García de pioneros, y la verdad es que es para mí un gran honor, una gran emoción estar aquí y ver lo que han alcanzado, Paola, doctores, con el laboratorio. Felicidades a todos y pues que lo disfruten, chicos, emociónense. Veo muchas caras chiquitas, estudiantes, emociónense. Esto es parte de lo que seguramente será el futuro de la radioterapia, esperemos que así sea, y pues bienvenidos, disfrútenlo mucho. Gracias.
¿Alguien más del Presidium desea dar unas palabras? Bueno, sin más, entonces cedo el micrófono al doctor Benjamín Pinedo Olvera, director de investigación del instituto, que declarará inaugurado este evento.
Muchas gracias a todos, bienvenidos. Para mí es un gusto que haya tantas personas interesadas en este tipo de alternativas terapéuticas que se están desarrollando en la actualidad. Los grupos internacionales en este tipo de alternativas terapéuticas que se están realizando, sobre todo en el área oncológica, particularmente en nuestro instituto, pues el área del cáncer cerebral, que es un área muy importante. Este tipo de radioterapia flash se ve muy prometedora, ya que puede liberar grandes cantidades de energía en sitios específicos en tiempos muy cortos, lo que hace que el daño a las células vecinas sanas o que no se desean dañar sea mínimo. Creo que es una alternativa muy interesante para desarrollar. Creo que hay muchísimos campos de investigación que se pueden desarrollar en este sentido. Particularmente mi área de interés es acerca de la respuesta inmune que se desarrolla, de este proceso inflamatorio que seguramente se verá reducido con este tipo de radioterapia flash, pero también todas las biomoléculas que se liberan por efecto de esta radiación, particularmente microvesículas, exosomas, que se liberan y que pueden promover la respuesta inmune ante estos tumores, potenciando aún así este efecto. Creo que sería un campo interesante de estudio con la radioterapia flash. Y bueno, seguramente estos estudios que se están haciendo ahora ya, no solo a nivel preclínico, sino también a nivel ya translacional, creo que dejará mucho en el campo de la oncología, particularmente de la neurooncología. Y bueno, sin más, y no quisiera seguirlos aburriendo con todo esto, seguramente todo esto se los van a dar con más detalle y a profundidad los expertos en el área. Y bueno, pues sin más, les doy la bienvenida a todos, les pediría se pongan de pie, y para que siendo las 9:21, quede oficialmente inaugurado este primer simposio mexicano de radioterapia FLASH. Sean todos muy bienvenidos.
Bueno, finalmente vamos a entrar a las pláticas que nos van a enseñar precisamente en qué consiste la radioterapia FLASH, cuáles son sus aplicaciones, cuál es la investigación que actualmente se está realizando y cuáles son los futuros líneas de investigación, así como la investigación translacional que se está llevando a cabo actualmente, por ejemplo, en Suiza, para que ya se aplique en pacientes oncológicos, como una oportunidad de tratamiento y sobrevida. Muy bien, vamos a empezar nuestro programa académico. A continuación vamos a tener la plática de la doctora Paola Ballesteros Cebadúa, ¿no? Cuyo título es Unlocking Ultra High Dose Rates, rollo académico, titulándose como doctora en Ciencias Biomédicas en la Universidad Nacional Autónoma de México y actualmente es investigadora en Ciencias Médicas aquí en el Instituto como parte del Laboratorio de Física Médica. Ella hizo una estancia de 2 años precisamente como motivo de aquel evento, ¿no? La foto que nos mostró, hizo una estancia en donde desarrolló líneas de investigación en radioterapia FLASH, principalmente los efectos radiobiológicos en el sistema nervioso central, en modelos de neuroblastoma y meduloblastoma. Así que cedo la palabra a la doctora Paola Ballesteros, que nos introducirá los conceptos de la radioterapia FLASH.
Ok, muchas gracias por la presentación. Muchas gracias a todos. Bueno, yo justamente les voy a platicar sobre qué es la radioterapia FLASH para todos los que no la conozcan y tengan un panorama en general. Nosotros sabemos que la radioterapia es uno de los tratamientos de cáncer más importantes actualmente. Aproximadamente el 50% de todos los pacientes con cáncer recibirán este tipo de radioterapia en algún momento de su tratamiento, y sabemos que desafortunadamente nada es perfecto en el tratamiento de cáncer y tenemos efectos adversos relacionados. Pero lo que se trata de lograr es que la ventana terapéutica que vemos aquí se abra, es decir, la distancia para una misma dosis de radiación entre los efectos adversos que produce esta dosis y los efectos de control tumoral sea lo más grande posible. Y en esto ha habido muchos esfuerzos a lo largo de los años para tratar de aumentar esta ventana terapéutica, y llegó principalmente la radioterapia conformal. Antiguamente los campos de radiación trataban de adaptarse, como vemos a esta vaca, trataban de adaptarse con cuadrados, y actualmente la radioterapia conformal utiliza varias tecnologías y equipos que tratan de proteger el tejido sano lo más posible, y gracias a esto la ventana terapéutica aumentó considerablemente. Sin embargo, actualmente la radioterapia convencional sigue produciendo efectos adversos a corto y a largo plazo, y tenemos los fraccionamientos estándar ya establecidos, donde normalmente se utilizan sesiones establecidas y tasas de dosis de aproximadamente 0.033 Grays por segundo, y estas son las tasas de dosis, y los tamaños de campo cada vez son más pequeños, pero las tasas de dosis están establecidas. Otro de los grandes retos de la radioterapia es el movimiento. El control del movimiento del paciente, como el control respiratorio, se trata de lograr mediante diferentes dispositivos, sobre todo cuando es radioterapia de pulmón, y este es otro de los grandes retos. Sabemos que la dosis de radiación física, es decir, la energía del tipo de tumor que se trate, de los factores genéticos, del ambiente tumoral, etc. Vamos a enfocarnos ahora en la tasa de dosis. Hasta ahorita sabíamos que entre más lenta la tasa de dosis, al menos en la clínica, normalmente lo que ocurría era que se reducían los efectos biológicos. Como vemos en esta escala, No se ve el apuntador aquí, ¿verdad? ¿Ah, sí? Ah, sí, perdón. Ya vi que sí, es que yo no lo veo. Entonces voy a voltear así mejor. Es que no sé si me van a escuchar. Ok. Ahí está. Ok, entonces aquí vemos cómo la escala de tasa de dosis, cuando lo damos muy lento, empezamos a competir con los procesos de reparación celular, pero también con redistribución, reoxigenación y repoblación. Pero por lo general, por ejemplo, ahí pueden ver las escalas de tasa de dosis utilizadas en la radioterapia IMRT, pero también las tasas de dosis convencionales en unidades monitor, como 600 y 1200, ¿en qué rango están? Entonces sabíamos que si dábamos muy lenta la dosis, como vemos en esa gráfica, lo que pasaba es que le dábamos tiempo a las células a reparar. Ahora, ¿qué pasaría si la tasa de dosis nos vamos no un orden de magnitud, sino cuatro órdenes o más, es decir, 1000 veces más rápido, como vemos ahí? Es decir, de 1 por 10 a la 5 o más veces más rápido. Eso sería la radioterapia flash. ¿Qué pasa? Bueno, pues uno diría, bueno, entonces habría menos reducción de los efectos biológicos, pues resulta que se vio lo contrario. Es decir, que también hay cierta protección en el tejido normal y esto es justamente la radioterapia flash. Es como dar un haz súper rápido a una tasa de dosis altísima para controlar los tumores. Entonces, ¿qué es la radioterapia flash? Es justamente aplicar radiación de tasas de dosis ultra alta en un tiempo muy corto, es decir, pasaríamos de tratamientos de minutos al orden de mili o incluso microsegundos, muy rápido. Y claro, está el asunto del movimiento. Si nos preocupa el movimiento del paciente, pues si estamos hablando de micro o milisegundos, pues el movimiento ya no importa tanto porque no le da tiempo ni de moverse, claro que hay otros retos, ¿no? Y después está la definición de lo que es el efecto flash. El efecto flash es lo que se ha observado en experimentos in vivo, en donde se observa que a estas altas tasas de dosis hay dos factores. Primero, se mantiene la eficacia antitumoral, es decir, los tumores siguen respondiendo, pero se protege el tejido normal. Es decir, se reducen las complicaciones secundarias asociadas a la radiación. Es decir, lo que se logró con estas tasas de dosis es abrir la ventana terapéutica. Históricamente, estas ultra altas tasas de dosis se habían utilizado en experimentos en los años 70 y 80, donde se dieron cuenta justamente de que usando muy altas tasas de dosis había cierta protección. En en esta gráfica en particular vemos que a diferentes tasas de dosis, por ejemplo, la baja de 0.033 y la alta, vemos el efecto de efectos adversos en la piel en este experimento y vemos como el grado de adversidad es entre la reacción más adversa o menos adversa. Entonces aquí vemos cómo la reacción tardó mucho más tiempo en aparecer, perdón, no es más adversa o menos adversa, sino el tiempo. Entonces vemos cómo tardó más tiempo en aparecer para menor tasa de, perdón, 0.033 Grays y 0.66, es que no veo el mouse, no sé si me pueden ayudar, porque sí está muy difícil hacer el pointer. Creo que ya lo logré, ¿o no? Aquí está, ya, ok, perdón. Entonces, bueno, aquí como les mostraba, vemos que hay una protección. Cuando aumentamos la tasa de dosis, hay una menor reacción de la piel. Y en general, esto se ha visto en otros experimentos también muy antiguos. Lo que pasó en esa época es que la gente pensó, bueno, si estamos protegiendo las células, pues vamos a proteger también el tumor. Y lo que ocurrió es que durante mucho tiempo esto se quedó en stand-by. Hasta que justamente el grupo de la doctora Bosenin aquí presente y Vincent Fabodon hicieron experimentos en pulmón buscando fibrosis pulmonar utilizando ultra altas tasas de dosis. Y ahí fue el redescubrimiento de la radioterapia flash, justamente utilizando un linac de electrones. Lo que ellos querían estudiar era la fibrosis pulmonar. Muchas gracias. Así está mejor. Lo que ellos querían estudiar era la fibrosis pulmonar y lo que observaron, como podrán ver en este corte histopatológico, es que a tasas de dosis convencionales, como las que vemos aquí, no existía, bueno, se ve la fibrosis y a tasas de dosis ultra altas se ve casi igual que los controles. Entonces, aquí fue cuando se dieron cuenta que algo estaba pasando, daban la misma dosis, pero mucho más rápido a una muy alta tasa, y la fibrosis no se observó. De hecho, este año se celebran los 10 años de este primer paper que se publicó, donde es el redescubrimiento de la radioterapia FLASH, y a partir de este paper de la doctora Bosna y Vincent Fabodon, empieza toda esta serie de investigaciones para redescubrir qué está pasando con las ultra altas tasas de dosis y la respuesta biológica. Actualmente este efecto protector del tejido normal se ha probado en muchas especies, incluyendo ratones, cerdos, gatos e incluso peces, y se ha probado no solamente con electrones, sino también con protones e incluso fotones. Esto se ha probado también en tejidos normales actualmente y también en tumores. Sin embargo, hay algunos estudios que vamos a mencionar, como los que están aquí, que no encontraron este efecto. Entonces, en general, estamos viendo que de alguna manera las ultra altas tasas de dosis protegen las células normales, pero no protegen los tumores, y como les decía, esto se ha probado para muy diferentes tipos de radiación. ¿Cómo se ve esta protección del tejido normal? Se ha visto que hay un daño reducido del DNA, es decir, como podemos ver, estos son varios estudios que lo reportan, pero por ejemplo, en células de las criptas intestinales se ve este marcador gamma H2AX de daño del DNA que está reducido en el caso de FLASH, pero no así en el caso de la radioterapia convencional. También se ha visto una reducción en la muerte celular, como vemos en este experimento, también del grupo de Fabodon, donde vemos que con túnel o caspasa 3 se ve la muerte celular, y de nuevo vemos como en el caso de FLASH hay menor con respecto a los controles, o la radioterapia convencional. También se ha visto, como nos va a platicar más tarde el doctor Limoli, una protección de la proliferación celular, por ejemplo, a nivel de la neurogénesis y de otros nichos de proliferación celular, donde la proliferación se preserva a ultras altas tasas de dosis, como podemos aquí ver en el marcador de doble cortina, que es un marcador de neurogénesis, de maduración de las neuronas. Entonces vemos aquí como los controles de nuevo y los flash son prácticamente idénticos. También se ha visto una reducción en la respuesta inflamatoria, como también un trabajo que seguramente nos platicará más tarde el doctor Limoli, donde se ven marcadores de inflamación, como es el CD68, que es un marcador de activación, y va un marcador de microglía, y vemos cómo en el caso del convencional está muy elevado y no tanto en el caso de FLASH. También se ha visto protección a la vasculatura, es decir, la radiación también daña los vasos sanguíneos, y vemos cómo hay, en este estudio, es un marcador CD31 de vasos sanguíneos, vemos cómo hay una reducción en el diámetro de los vasos en el caso de CONF, y no es el caso en el caso de FLASH. Entonces, en este diagrama de este artículo de la doctora Bosna podemos ver que en la radioterapia convencional hay, al parecer, un mayor daño al DNA, hay menos daño en el caso de FLASH, pero también tenemos menor daño vascular, preservación de las células progenitoras, menor inflamación y preservación de la función de los diferentes órganos. Además, se ven algunos otros efectos muy notables, como en el caso de la peroxidación de lípidos. Las membranas que están hechas de lípidos con la exposición a la radiación pueden sufrir lipoperoxidación, y se ha visto que después de FLASH la lipoperoxidación está reducida, como se puede ver aquí en este experimento de Vincent Frodebo, donde se ve que con liposomas de lípidos irradiados se ve justamente una muy reducida lipoperoxidación en comparación con la radioterapia convencional a diferentes dosis. Entonces vemos un efecto muy claro. También en el caso de daño mitocondrial, por ejemplo, aquí se ve que hay una menor afectación de las mitocondrias, de igual manera en el caso de FLASH con respecto a radioterapia convencional. Entonces, en resumen, vemos una clara respuesta protectora del tejido normal. ¿Qué hay de los tumores? Bueno, como les mencionaba, se ha visto que no se protegen los tumores, ¿no? Que esa es la parte más inesperada. No se protegen las células tumorales con las ultra altas tasas de dosis. Esto ya ha sido probado en células de cáncer de mama, de cabeza y cuello, de pulmón, de glioblastoma, células escamosas, sarcomas y como vamos a ver el día de hoy, de méduloblastoma. Y esto se ha visto con electrones, con protones, con rayos X y con iones de carbono. Entonces vemos que no hay un efecto protector. También otra de las cosas que se ha preguntado la gente es, bueno, ¿y estos han sido solo una sola dosis? ¿Se verá la misma protección si hacemos fraccionamientos? Bueno, pues al parecer sí se puede ver en algunos fraccionamientos. Por ejemplo, aquí vemos como esta es una medición de la protección de la cognición. Entonces vemos que aquí FLASH es igual que los controles a esta dosis, pero si se aumenta demasiado la dosis, pues ya se pierde esa protección. ¿Ok? Pero aquí vemos cómo en fraccionamiento, si esta dosis la damos fraccionada, se recupera la protección del cerebro, o en este caso de la memoria. Y aquí vemos igual, con ciertos fraccionamientos se puede ver esta protección y con otros no. En particular, seguramente el doctor Limoli les va a platicar sobre el artículo más reciente, donde también se ve que el fraccionamiento protege la respuesta neurofisiológica eléctrica de las neuronas. Entonces, bueno, como yo les decía, no todos los estudios que han utilizado ultra altas tasas de dosis han observado esta protección del efecto FLASH. De hecho, aún estamos tratando de entender cuáles son exactamente los parámetros y las condiciones, tanto de la tasa de dosis como de la duración del tratamiento, como del ancho de los pulsos y las diferentes características de los haces de radiación que pueden generar este efecto. Aquí se puede ver en esta gráfica cómo, por ejemplo, para tratamientos más prolongados de 1 segundo, que duraban más de 1 segundo, con ultras altas tasas de dosis, en el caso de electrones, ya no vieron el efecto FLASH y sin embargo estos sí lo observaron. Pero también, como podrán ver, hay algunos casos de protones que sí lo vieron, otros que no, y también algunos casos de fotones que también sí han observado este efecto. Entonces, como podrán ver, esto se está tratando de entender. Las reacciones de la radioterapia dependen de la primera fase inicial de interacción de la radiación con la materia, que es la parte física. Después tenemos la parte físico-química y justamente en esta parte química es el tiempo en el que se deposita la radiación FLASH. Y después la convencional estaría llegando incluso hasta la fase biológica. Entonces, como yo les decía, estamos hablando de una nueva escala de tiempo en donde están sucediendo las cosas mucho más rápido. Aquí podemos ver justamente los parámetros que pueden ser claves en si se presenta el efecto FLASH o no se presenta el efecto FLASH, que puede ser la duración de los pulsos, el ancho de los pulsos, qué tanto la frecuencia en la que se dan los pulsos, y todo esto está en investigación. Finalmente, esto no solamente se ha probado en animales, ya se probó por primera vez en pacientes. Esto es una publicación del 2019, en donde justamente en el Hospital Universitario de Lausanne, en Suiza, se probó el primer paciente. Este fue un estudio de seguridad y factibilidad que salió bien, pero ya actualmente se han hecho otros protocolos clínicos para evaluar esta tecnología, si puede beneficiar a los pacientes. Por ejemplo, en Cincinnati está el FAST-1 y el FAST-2 en metástasis de hueso, el FAST-1, y seguramente la doctora Tsutsu nos platicará de cómo esto está siendo, empezándose a probar tanto en Suiza y en particular en Ginebra. Entonces, bueno, en general, esto, como les digo, es tecnología muy nueva y lo más interesante es que está en camino a la traslación clínica. Todavía existen muchas preguntas que nos van a ayudar a que esto llegue a la traslación clínica, como asegurar, por ejemplo, la precisión de estos tratamientos que son tan rápidos, la conformalidad de estos tratamientos, pero sobre todo también retos para física médica como la dosimetría. Sabemos que los detectores perdón, tienen una dependencia con la tasa de dosis, muchos de ellos, y cuando sube la tasa de dosis, fallan para medir la radiación. Sabemos también que algunos detectores sufren de saturación o no tienen resolución temporal para ver pulsos tan pequeños, y tampoco existe un protocolo de estandarización, es decir, no hay protocolos para calibrar a estas ultra altas tasas de dosis, por ejemplo. Entonces, todo esto está creciendo para poder llegar a la parte de la traslación clínica. También hace falta información sobre muchos otros tipos de tumores todavía, combinaciones con quimioterapia, y sobre todo estamos en proceso de entender los mecanismos de por qué en algunos casos sí se ve, en otros casos no se ve, y por qué se da el efecto flash. Y esto les voy a platicar más adelante. Y esto nos va a ayudar para poder optimizar los tratamientos. Finalmente, decirles que ya hay muchas empresas que están desarrollando equipos de radioterapia flash, entre ellos está Varian, IVA, que están apostando a protones flash, pero también, por ejemplo, está este desarrollo de fotones flash, por ejemplo, que es el desarrollo del equipo de Billy Liu en Stanford, que están construyendo este equipo que se llama Phaser. Y también tenemos los equipos de electrones, por ejemplo, la empresa TerryQ está apostando a electrones de ultra alta energía para poder aumentar la penetración de los electrones y tener electrones flash. Es decir, esto es tecnología que ya se está empezando a desarrollar para que pronto esté disponible para la parte clínica, y desde luego va en paralelo avanzando todo desde la parte básica de investigación en radiobiología, en radioquímica, con la parte de física y con la parte de la aplicación en pacientes. Pues muchísimas gracias, no me queda más que agradecer, y si tienen alguna pregunta, con mucho gusto. Si alguien tenga alguna pregunta.
Gracias. Quisiera saber, buenos días.
Gracias.
Hacen los de cerebro. Hay
Sí, bueno, sobre esta parte hay muchos estudios que están en progreso, y yo creo que la plática de la doctora Bosno va a ser justamente sobre tumores de radioresistentes. Entonces yo creo que ella es la más indicada para hablar de eso.
Bueno, felicidades, muchas felicidades. Quisiera agregar solamente dos cuestas. La primera es agregar a lo que dijo ya el doctor Lárraga. Pionera en México de la terapia flash, eso faltó decirlo. Y segundo, o de otro tipo de investigación que den cuenta o que avalen los resultados clínicos que han hecho con las células.
¿Te refieres a modelos matemáticos?
Sí, matemáticos, programación, Gene4. Me acuerdo que estuvimos viendo algo de Gene4 porque te atendía algo del DNA. Quería apuntar.
Sí, en general ha habido muchos trabajos de simulación Monte Carlo con diferentes softwares, y curiosamente han encontrado resultados quizás no tan consistentes ¿no?, con lo que se ve en biología, pero es interesante porque evidentemente los modelos no toman en cuenta mucha parte de la biología. Algunos sí tienen resultados más, digamos, consistentes y otros no, pero sí, hay mucho trabajo en modelado matemático actualmente sobre FLASH. Muchas gracias.
Yo tengo una última pregunta. ¿Qué tipo de radiación es la que más genera una ventana terapéutica más amplia? ¿Los electrones, los fotones, las partículas cargadas, pesadas?
Esa es una muy buena pregunta. Yo creo que todavía no está claro si existe una ventaja con respecto a una u otra. Eso yo creo que todavía no se sabe con claridad. Lo que se sabe es que se ve el efecto y que se ve en condiciones similares, en dosis similares, eso ya se hizo, o sea, es decir, en modelos similares, usando el mismo modelo, el mismo tipo de ratón, la misma dosis, etcétera, se ven respuestas similares, pero ya si la magnitud de la respuesta es un poco mejor en uno o en otro, desde mi punto de vista eso todavía nos falta más investigación.
Bueno, le damos gracias a la doctora Paola Ballesteros Cebadú. Bueno, para continuar con estas interesantes pláticas y ir asentando precisamente qué es la radioterapia FLASH, cómo puede ayudar la radioterapia FLASH a nuestros pacientes, pues a continuación tenemos una plática muy importante que es del profesor Charles Limoli. Él es investigador y profesor. Su trabajo se centra en definir las consecuencias de los cambios inducidos por el tratamiento del cáncer en las funciones del sistema nervioso central y en desarrollar intervenciones farmacológicas, genéticas y basadas en células madre, muy importante, para resolver estas disminuciones cognitivas asociadas al tratamiento. Más recientemente, su grupo ha definido algunos de los mecanismos beneficiosos de la radioterapia de ultra tasa de dosis, llamada FLASH, en el cerebro irradiado, iniciando un importante programa de investigación financiado por el NIH en Estados Unidos. Muy bien, a continuación entonces cedo la palabra al profesor Lomeli, cuya plática es A Timeline of Progress Investigating the Flash Irradiated Brain. Por favor, profesor. Please.
Gracias, amigos. What we're studying is everything you see in front of you. So we're looking at very early processes, everything you see in front of you. So we're looking at very early processes, and then we're looking at things that happen at the physical, chemical. So this provides a backdrop of the challenge of why everyone in physics, and chemistry, biology, and the clinic have to come together and talk about this in vivo observation, an observation that, as opposed to neutron and photon and proton flash units, I'm not going to get into the physics today in my talk, but what we found is that surprisingly, when we can deliver the same dose at really fast dose rates, as you've just heard, we could minimize normal tissue toxicities across every normal tissue pretty much studied to date, but we don't spare the tumor. Otherwise, it would be no use to us. So we have equal efficacy in anti-tumor responses, and this is just to show you that this is broadly applicable across many preclinical model systems, across all the of clinical treatments and how we're going to move the oncology field forward. And so I've spent my career studying the neurocognitive complications of standard of care, conventional slow dose rate radiation, which is pretty much 99% of the ways we treat secondary and primary malignancies in the brain. And what we found is that, we can get variable survival rates, a little bit better, a lot better in the kids. It's not so good with people with glioma. Ways to fix neurocognitive complications. So I spent a lot of time in my career when I first got to UCI looking at regenerative medicine approaches for fixing things. We would transplant human stem cells in the brains of irradiated rodents. We've modified various pathways that impact inflammation, and we've found that basically a lot of strategies, for example, microglial elimination, If we lower inflammation, we can produce these global benefits of we can protect the brain from the adverse effects of radiation through a variety of about 8 or 9 different techniques. But these are super complicated. And what I'm going to show you now is we can accomplish the same thing in microseconds. You don't have to be a neurosurgeon to use FLASH. We get the same benefits. Okay? And so I'm going to give you the backdrop of what we started with. And really one of the most important studies that was done in Dr. Vozanon's lab was, look, I'm going to walk you through the history of this a bit. We didn't know anything about this, in the brain at least, until about sometime after about 2019, 2017. And Pierre did a series of studies where when we had low dose rates, and we have a recognition ratio means the higher on this y-axis, the smarter the animal is. Low dose rates, the animals aren't very smart. They don't perform well on this task. When we go to the high dose rates, we find that the animals act as if they weren't irradiated. And so we were able to define some dose rate cutoffs for the neurocognitive benefits after FLASH, and there's some intermediate values. And so when I first heard Dr. Vozanon give a FLASH talk, I was in the front row and I was shaking my head, no, Dr. Vozanon, I don't believe it. So we went up, we started a collaboration. She sent her graduate student to my lab, and we put one of these first papers together, which was really the backdrop of getting the FLASH story going in the United States. And what we did, we started with a single dose, and I had developed a lot of neurocognitive assays in my lab. So what's important here, I'm going to show you a lot of data. So let's keep it really simple. I'm always going to show data where on the far left, the black bar, are the unirradiated controls. In the middle, we're going to talk about the animals that were given the slow conventional dose rate. And on the right, we're going to look at the animals that were given the high FLASH dose rates. And what you can see, depending on a specific task, whether it's the novel object recognition or temporal order, now it doesn't matter whether you believe this is good or bad, but what you'll notice is that the controls always seem to track much more closely with the FLASH than with the ones in the middle that were given the slow dose rate. And so we have some other tasks down here that test measures of, for example, depression or anxiety. Again, you can see the controls match the FLASH much more closely than conventional. So these measures were done from 1 to 6 months after radiation. And then if we don't want to rely on tests that query an animal's ability to recognize novelty, which are spontaneous exploration tasks, we can go to tasks that are much more similar to human anxiety disorders like PTSD and look at extinction memory. And this is an important test because it doesn't involve an animal moving around. So we can give a series of tones in a mild foot shock, and the animals will freeze. This is a response to predation. And so they know when they hear this tone, they're going to freeze. Over subsequent days, we can put these animals in the chamber, but give the tone, but no shock. And after a while, a smart animal remembers if he hears the tone, well, I'm not going to get the shock anymore, so he doesn't freeze as much. This is called extinction memory. You notice that the animals that conventional dose rates, they still freeze, and this is exactly like PTSD in humans. So FLASH is just, again, like the unirradiated controls, and this deficit, which is the extinction test here, low freezing in control, low freezing in the FLASH, persists months to years after exposure. This is why people that come back from war have a long-term problem with PTSD. So FLASH is showing some remarkable benefits in neurocognition. So again, this is after a single dose of 10 gray, and what we showed here is if we look here at astrogliosis on the left, or microgliosis on the right, again, the controls are very similar to the FLASH. In other words, FLASH really minimizes the level of reactive astrocytes, and FLASH, whether we look at 1 month or 6 months after exposure, really minimizes the number of reactive microglia. So, low neuroinflammation, benefits to cognition. We also used animals that we were able to, that had inherently fluorescent neurons, and we were able to take slices of these brains, and we have a couple of relatively complicated algorithms through the Amara software suite, where we can trace from the soma down here, and we can track dendritic branching, dendritic length, a number of geometric parameters. And again, you can see here when we look at the length of the dendrites, etc., the flash and the controls, it's as if the animals weren't irradiated. And if we look down here, if we zoom in on this, and we look at these little red images, these are the dendritic spines, which are the structural correlates of learning and memory. So conventional irradiation here strips the spines off the dendrites. And the animals that have the least number of dendritic spines show the poorest performance on neurocognitive tests. So again, the flash irradiated animals, pick a parameter, it doesn't matter, as if they weren't irradiated. So flash is preserving host neuronal structure. So this was a single dose study. Strengths of the study, we did a whole gamut of neurocognitive testing that over the long term. The weaknesses of the study was single dose, and we don't treat people with single dose, and there was no tumor. So what we wanted to do then is look at the neurocognitive benefits of hypofractionated flash radiotherapy in adult mice. And so now we go to that 3 times 10 gray regime. So our total dose is 30 gray, given in 3 fractions, Monday, Wednesday, Friday. And again, we looked at very long times after irradiation. And we did some more fancy cognitive tests, and I don't want to get wrapped up too much in the details of the neurocognitive testing here, but what you can see here, we have an object in updated locations test, and we have a series of objects that we start with 2. We move A2 to A3. So this here is the same thing as what we'd call a novel place recognition test. And then we try to confuse the animal by adding more tests. And what this does is allow us to track multiple associative memory traces in a single test. So we're increasing the cognitive load or the rigor of the task. And what we can see, whether we look at males or females across these different sessions, what you'll notice, if we just focus on this and this, again, the controls are much more similar to the flash, and we have the decrements. Remember, lower on this y-axis, the animals don't perform as well. So these were some much more complicated tasks that we ran on both sexes. So flash isn't preferentially beneficial to one sex or the other. And we can do other tests here. So here's a novel object recognition task. We didn't quite get the robust effects on a light dark box here or with the females, but we got some good effects with the males here where the flash was similar to the controls. And then when we look at the extinction testing again, we get the same thing. This is months after radiation, where the animals that were tested after extinction testing, they can't dissociate that tone from the foot shock. So we were able to substantiate very similar data from our single dose studies with our fractionated study of 3 times 10 gray. So let's see what else we can find out about these animals that were given a pretty high total dose in 3 fractions. What we can see here is what we wanted to look at now is the microstructure of the synaptic cleft. And so we're looking at some Bhutan, from pre- and post-synaptic Bhutan, Homer 1 and boson puncta. And what we're trying to look at here is looking if there's a change in the amount of these pre- and post-synaptic proteins. We get some trends here in the females, not so much in the males, but importantly with the synaptophysin, this is a presynaptic vesicle, we get preservation of synaptophysin after flash and control, and the conventional knocks it down. So I would argue that some of the effects we're seeing really come down to the synaptic level. And if we wanted to substantiate some of the data we found before, again, this is with the hypofractionated regime. If we look at CD68, so this is our marker of our reactive microglia, a marker of, let's say, a surrogate of neuroinflammation. And we look at, for example, toll-like receptor 4, we can see after conventional, there's lots of these reactive microglia. There's an activation of the TLR pathway. But after flash, we have this remarkable suppression of these neuroinflammatory pathways after a pretty high dose. And so again, we're confirming what we found with the single dose studies, with our fractionated studies. And so now let's go, into perhaps the second most important functional effect in the brain. If you have one neuron and you're not impacted at all by cognition, who cares? So in our lab, we're really interested in the types of things that change cognition first. And then if we look at neurotransmission, which is the basis of our memory and daily activities, this is another critical functional output of the CNS. And so we have the privilege of working with one of the most talented electrophysiologists in the world. And what she can do is she can stimulate in one region of the brain along the Schaefer collaterals, and she gives a burst of these theta spikes. And then she measures many synapses away whether that stimulates or facilitates depolarization of neurons downstream. And so what this measure is, this long-term potentiation, is what we call in the neuroscience field synaptic plasticity. And what we can see is when we stimulate in one area and see if we get more firing, right, this something that we believe facilitates long-term memory, we can see that the conventionally irradiated animals, this long-term potentiation is inhibited. This is super important. But after control and after flash, they're superimposable. So this has turned out to be one of our most robust functional outputs in the brain. And we can pick this up after a single dose of 10 gray. It's absolutely no difference after a 20 gray additional dose. So our 3 times 10 gray animals at the electrophysiologic level, there's a big inhibition of LTP after conventional, as if the animals weren't irradiated when we measure long-term potentiation. And one of the more important things we just published with our group, people were worried that the flash effect could only be demonstrated after relatively high single or high hypofractionated doses. And he did a similar experiment where now we look in 2 regions of the brain. We look at the hippocampus, where we stimulate and record along the Schaefer collaterals, or we can look in the prefrontal cortex, where in the infralimbic 10 doses, at least at the electrophysiologic level, it's as if they weren't irradiated. So this was super exciting to us. And so where we wanted to go from here is, this was a study where we were able to demonstrate the long-term benefits of a hypofractionated regime in adult animals. And as you've seen from Paula just before, of course, one of the weaknesses of this study was we didn't have a tumor. And I'll go over this quickly because this is some data from Pierre Montet and Bruel and Dr. Vozenon's lab. We applied the same 3 times 10 gray radiation. We were able to slow down the tumor growth. We were able to improve the survival. And most importantly, we maintained the neurocognitive benefits after flash compared to conventional dose rate. So now we can't do all the long-term neurocognitive testing because these are tumor-bearing animals, but in some tumors we implanted, this dose was curative. And so we're able to show that we're able to do the neurocognitive testing in tumor-free, tumor-bearing animals. And so the data that I've just shown you now was in adult animals. And so we're pretty interested in this is the work we've done with Paul and Dr. Vozenon. What if we go to a super radiosensitive juvenile animal? And so when we started this, we weren't sure what the dose tolerances of a 2 to 3 week old animal, whether we can give 3 gray, 8 gray, 12 gray, and what would be too much. But over the course of these studies, we were able to demonstrate that, as you'll see, if we gave a single dose of 8 gray, or we dropped the total dose of our prior fractionation study to 20 gray, we gave 2 doses of 10, we're able to implement this type of experimental design where we irradiate at a young age. We do a bunch of behavioral assays. We do some follow-up assays of electrophysiology, immunofluorescence, and this is the work of these talented people in my lab. We're able to show you, again, some data that we published a while ago. Super nice benefits in novel object recognition, and this was after a dose of 8 gray. We were able to spare the number of newly born neurons. These are the double court neurons that are born within 14 days. So if you're going to measure this, these neurons here were about 2 weeks old. And so we were able to preserve the double cortin. If you want to measure neurogenesis, then you have to load up the cells with a proliferation marker. In this case, it's bromodeoxyuridine. And then you have to look for the cells that pick up the proliferation marker and stain for a mature neuronal marker, in this case, NuN. And when we look at the cells that are both BRDU and NuN positive, we find out now, so these neurons now are 30 days old. So when they're born, it takes 30 days to express NuN as opposed to 14 days for double cortin up here. So we got a sparing of the neurogenic niche. So this is something other people have found in the gut and the skin, and perhaps provides some of the basis of at least a normal tissue sparing in the flash effect. We're also able to spare growth hormone levels in these young animals, suggesting that maybe the endocrinopathies that young patients that receive cranial radiation might be ameliorated in the flash setting. So when we do the neurocognitive testing in the young animals, I won't belabor this. You've seen this again. Again, if we look at the OUL test or novel object recognition test, we get the same data across males and females. Again, it's if the animals weren't irradiated. So these measurements were done long after radiation. And again, if we look at a more complicated test as we see here, we get the same benefits in the supersensitive, radiosensitive juvenile animals for the neurocognitive testing. And if we take the juvenile animals here and ask Annie to do some more electrophysiology, again, control, flash, indistinguishable. But when we give them the conventional, the inhibition of LTP is readily apparent. So if we dig down into the young animals here, now we look at this synaptic integrity, we get a little more interesting results here. So now we have a preservation of the synaptic bouton here. We're looking at the juxtaposition of Homer 1 and bassoon at the synaptic cleft. And this is, again, by super resolution microscopy. We get a bit of sparing in the structural integrity of these two markers of synapse. And again, we get nice sparing of our presynaptic synaptophysin across the brain. So we get a lot of minimization between male and female mice of the neuroinflammation, the reactive microglia. So we don't have to dissect these images too much, but we're doing lots of slices in these animals. And again, you see the common themes that are coming out. We have a preservation of LTP, a minimization of neuroinflammation, a preservation of host neuronal structure, and perhaps a little bit of new data. We're also getting a sparing of water channels that are closely associated with the microvessels in the brain. And so here, between female and male mice, we get a robust effect here. Perhaps the sparing of these aquaporin channels is facilitating exchange across the blood-brain barrier, and maybe one of the things that's common across all normal tissue sites is, of course, the vessels. And so there's data from other groups showing that maybe the vessels are one of the critical targets. And so I'd like to wrap up now, and this could be a topic for the panel discussion later. We've been, Dr. Rosenone and all of us have been going back and forth about what the mechanisms are. And in my humble opinion, everything on the top here are the mechanisms that are most likely. So we're thinking preservation of the stem cell niche, okay? Of course, what's the problem here? If we have normal stem cells spared, then maybe we're sparing the cancer stem cells. So then why do we have isoefficient tumor kill? So this has a caveat. You saw some data that Paula showed about lipid peroxidation. So maybe lipids are the target. We have some protein targets, and this is something that we could talk about in a bit. We're leaning to the idea that maybe there's a specific class of proteins that might persist throughout your lifetime that are the critical targets in the flash effect. And then there's some data showing that there's a change between oxidative phosphorylation and glycolysis. So maybe a fundamental change in the way cells metabolize and go throughout their homeostasis is something that benefits normal tissues, but it's less consequential in tumors. Down here, I'm going to put to rest these mechanisms because they're not involved. This idea of radical recombination, there's been enough people modeling this, it drives me crazy. This is not what's going on. The idea that FLASH cares about what the primary sequence of DNA is, no. There's enough tumors we've studied and they're all killed equally and they're vastly different genetically. DNA damage and repair? Not likely. It's not due to DNA damage repair, despite some of the evidence that people have published. That's not one I'm going to put my money on. We have partial blood irradiation. So this is an interesting idea where if you flash irradiate your arm, it's only a microsecond, so only blood that's right there resident during the time of radiation is going to be irradiated, where if you irradiate that same region of your arm over the course of a few minutes, circulation drives all the cells through the area, so much larger volume if your blood's irradiated. So maybe there's a critical target in the blood that's minimally irradiated at flash as opposed to standard of care. Data that we've got that Dr. Vozanon's lab here suggests that that's probably not the case, because if it's some sensitive population of T cells or B cells or whatever, she's done a very nice study in collaboration. Dr. Emmerich has done the study and published this in the Red Journal, where it doesn't appear as though adaptive immunity is evolved because we get the same level of tumor kill in progressively immunocompromised mouse models. And these were done with multiple tumor types, both orthotopic and xenografts. And then lastly, a favorite of the field is this oxygen depletion, where the idea is that a sudden burst of radiation can transiently deplete oxygen and produce a transient radioresistance, which would be obviously volume dependent. There's been enough data now, and I'm not going to get into all the evidence behind it, that suggests that that's simply not the case. And so really where we're at now with the mechanism is that I think what FLASH has done, it's given us a physical tool that just played into the hands of radiation science, all right? It's given us the ability to discriminate something unique between cancer and normal tissue. It's given us a tool similar to what the monoclonal antibody and the restriction enzyme gave to molecular biologists. We didn't know that delivering radiation super fast would have all these benefits to normal tissue that the tumors didn't seem to care about. And so where we're thinking about this now is, again, with what I've mentioned, there's a super specific class of proteins that we think are the critical target. And this super special class of proteins are not in any tumors. It's virtually impossible for them to be in tumors. So think protein, think special targets, forget about oxygen depletion. And so where do we stand now with the summary of what I've told you? So we've gone over a lot. And so remember when we started this, I started 4 or 5 years after my colleague, Dr. Vozanon. We didn't know much about all the issues with the brain. So we've been able to demonstrate that single and fractionated doses of conventional and flash, the conventional routinely leads to adverse outcomes, whereas with the single or fractionated flash, we're able to preserve and minimize neuroinflammation. We'll be able to preserve long typically not at the flash dose rates. And so
exactly.
yeah. So the conventional that we're delivering is delivered in a pulse that's super slow, like over the course of 10 gray per minute. Okay, and what we're doing in the flash, we're giving our 10 gray in 1.8 microseconds. That's the majority of the information that I presented. So it's a single pulse of electrons delivered in 1.8 microseconds.
And the conventional, if it's a conventional LINAC, it's many pulses because of the time structure. Thus, the dose rate for the conventional, isn't it much higher than 0.033 grays per second?
Or dose within the pulse? And this is a super important question everyone is investigating right now. What I can say for the animal experiment is if we are using a conventional LINAC with a pulse structure, a continuous photon beam with continuous irradiation, a continuous proton beam with continuous irradiation, we retrieve the exact same impact at the neurocognitive level. So all those beams, when they are delivered in the range of an average dose rate of 0.1 gray per sec or less, or more, slower, okay, they retrieve the same impact and alter the cognition in the animals.
Muchas gracias. ¿Alguien más tiene una pregunta?
Do I wear this now?
In Spanish, so you don't have problems with translation. Estudió los distintos niveles del hipocampo para determinar el long-term potential, o solamente fue un solo nivel en sus experimentos?
Only a single level, and they. Yeah.
What level? ¿A qué nivel?
So we're measuring for the LTP studies?
Yes.
That was on the Schaefer collaterals.
Okay.
But when we're looking, so for the neuronal preservation, we're looking in the dentate gyrus, the granule cell neurons, and when we're looking at neuroinflammation, we're looking at the pyramidal, the molecular layer on the CA1, for example.
Okay. But what level, ¿cuál fue el nivel que estudió entonces? Porque digamos hay una diferencia en estructuras en el hipocampo para determinar el long-term potential o los potenciales del término largo.
Measurements we have are a long time after all consolidations take place, so all the amps.
Interesting talk. LTP have different.
Most of those changes, Javier, come very quickly after radiation, and we can't get the animals back from Stanford or Switzerland in time. So it's kind of a limitation not having a flash irradiator in place.
Oh yeah,
so,
sure.
Yes, would be interesting to see what types of NMDA antagonists or AMPA antagonists might eliminate the benefit of the flash and drop down to conventional. But those studies have to be done within 2 weeks. So what we have shown is if we get the animals back, for example, as quickly as possible to analyze. So remember, we don't have the flash. When we analyze the effect LTP 2 weeks after radiation, there's no inhibition of LTP after conventional. So this emphasizes that there's a time it takes to manifest this decrement in LTP, which is also the same thing we know after cognition. When patients don't get up for the radiotherapy table impaired, it takes many months to manifest these decrements, suggesting there has to be some type of turnover that the proteins that were damaged have to turn over at some level, and it takes at least 2 weeks to get that turnover for the LTB inhibition. And we've also shown that the benefits to neurogenesis or double cortin cells takes at least 2 to 3 weeks after radiation to do. So this really begs the question of what early measurements after irradiation, at least in the brain, portend what happens late after. And I argue that it's all a mishmash, that what you study early on is very difficult to translate to what happens many months later. Not that it's impossible, but it hasn't been a super fruitful line of investigation.
Okay, thank you.
Muchísimas gracias al profesor Limoli. Por favor, un fuerte aplauso. Y bueno, creo que el simposio está cumpliendo su objetivo, ¿no? Hacer un tema nuevo. Hay más preguntas que respuestas, así que vamos a continuar. Yo creo que estamos aprendiendo muchísimo el día de hoy. A continuación, pues bueno, creo que va a ser una breve introducción que no le hace honor a la profesora. Bueno, a continuación tenemos a la profesora Marie-Catherine Bosenan, con su plática Flash Radiotherapy, Beyond Normal Tissue Sparing and Opportunity Against Resistant Tumors. La profesora Bosenan, como ya lo mencionó la doctora Ballesteros, pues bueno, redescubrió y reintrodujo el concepto de la radioterapia flash, ¿no? Es pionera y punta en estas dos líneas de investigación y es un honor tenerla aquí con nosotros junto al profesor Limoli. La profesora, pues bueno, ha abierto muchos laboratorios, 2 en Francia, 1 en Suiza ya es estructurado y actualmente es profesor invitado en la Universidad de Ginebra, el Hospital Universitario, abriendo un nuevo laboratorio. Es el Laboratorio de Innovación en Radiología Aplicada a la Radioterapia. Actualmente su línea de investigación evidentemente es la radioterapia FLASH y cómo combatir tumores como los tumores cerebrales, pulmonares y de piel, así como los efectos adversos en el tejido normal. Pues bueno, damos la bienvenida a la profesora Bosenan.
Well, thank you so much for having us. I'm really pleased, and I must apologize. My Spanish is non-existent. I never learned it. Can understand it a little bit since I'm French-speaking originally, so kind of a Latin language. I'm really happy to be here upon the invitation of Paula and Javier. We had Paula and Javier in the lab with us for 2 years, and it was a real pleasure to have them. We miss them so much since they left. We really would like to have them back. The 2 of them, the 3 of them, by the way, including Fernand as well. So Charlie told you quite a lot, and I guess it was an AV morning. With loads of information related to the mechanism of flash irradiation. And I will kind of switch gear a little bit. I will go a little bit closer to some kind of clinical investigation and how we can apply and use flash in the clinic. I would like to know from the audience who you are a little bit so that I can adjust what I'm going to tell you a little bit. How many of you are radiobiologists? How many of you are medical physicists or physicists? Okay, majority of you. And radiation oncologists? Okay. Neurobiologists? A couple of you as well. Okay, so I won't talk too much about the brain, only a little bit. So yeah, let's have a look at what we have when we are using radiation to treat cancer. We are really aiming at eradicating tumors with the minimal toxicity at the normal tissue level. And our goal as radiation biologist and oncologist and medical physicist was really to enhance this therapeutic ratio. And in our field, we are pretty lucky because to do so, we have two angles. A biological angle that we can understand and really optimize in order to induce or reduce radiation sensitivity, induce it in the tumor, reduce it in the normal tissue, but we have also the technology angle, and it's what most of you are interested in. As you know, the irradiation procedure and the processes have evolved tremendously over the last 120 years that we have been using radiation therapy. So radiation therapy is a pretty old approach to treat cancer, but it has evolved tremendously from the beginning, where the irradiation, as Paula showed you before, was kind of a broad and non-target, to a very precise, targeted, and personalized therapy. So today, radiotherapy is very targeted, and it can be very precise, delivered as a personalized therapy for each different tumor and each different patient. Despite these big progresses over the time, we're still facing radiation resistance. So we still need to improve the way we're gonna deliver radiation therapy. And if we're looking at the imaging angle, and I guess that many of you have been working at that level, we are kind of reaching a plateau. There is not much more we can do with the targeting approach in order to improve this therapeutic window. Therefore, we need some new strategies, some new angles. And we have been thinking that those new angles would come mainly from the biology. And I was arguing that there was a lot we could do with the beam themselves, because globally, the irradiators, the machines that we are using in the everyday treatment, have not really much evolved in the last 50 years. They are kind of linacs with cavity, providing the same type of beams, and we have not been playing around with the beam itself. Whereas there is a lot of opportunities, different opportunities that we are now experiencing to do so. One of the big opportunity is to alter the special delivery of the dose. And there is a lot of work done on what we are now calling SFRT, and I won't be speaking about that, but it's a big field of research. Instead of going for homogeneous delivery of the dose, we will alter the special delivery and perhaps also be able to adapt the dose that we deliver to specific sensitive or resistant area in the tumor. And the other aspect that I have been working on the past 15 years is this aspect of flash radiation therapy. And I won't go too much more into the definition of what flash is, because it's still a little bit unclear what we are calling flash. There is still some work that remains to be done to characterize it at the physics level. That's why we need you around. But I'm going to show you what we've done. The first type of experiment we've been doing when I was back in France at the Institut Curie with my friend and colleague Vincent Favaudon, And when we irradiated brain of mice, I'm not sure you're going to see it. Well, it's better on the screen, by the way. Here we are irradiating a mouse at the brain level. And we irradiating this mice at conventional dose rate. And you see all the small dots that are hitting the cameras are the electrons that are produced when we are irradiating these mice. Here, we are delivering a 10-gray dose. And as long as I'm speaking to you, it's irradiating, irradiating, and irradiating. So you see that it takes a bit of time to deliver a single dose of 10 gray to a mouse. Now, if we go flash, don't blink. It's not irradiating, it's not. It's not. It's not. Here it is. Okay? So you see, this is pretty simple stuff. This is the difference in between conventional irradiation and this flash irradiation. Here, the dose was delivered with a LINAC, to answer your question. So both of them, it's a LINAC. Globally, the conventional irradiation was delivered with 1,500 pulses of electron, small pulses over a long time. And the dose here of 10 gray was delivered with one single pulse of 1 microsecond. So super short irradiation. And doing that, we are able, in an unexpected way, to widen the therapeutic window of ionizing radiation as we push the curve of the normal tissue complication probability toward the right. So the first thing that we've been showing was really a striking observation. This enhancement of the therapeutic window by pushing the normal tissue complication curve to the right. So the normal tissue are spared by flash irradiation. And this, as Paolo showed you already, was also shown very much in the past, in the 70s and in the 80s, in groups that were working in New York City, as well as in Manchester in the UK and in Oxford at the Gray Lab. It's super funny because some of them are still around, including Joyle and Hendry, who made the publication in 1882, showing that indeed ultra-high dose irradiation spare skin from the toxicity. But then what was they thinking at the time? They were thinking that it was a nice phenomenon that could not be very useful in the clinic. Because if you spare the normal tissue, you would spare the tumor. So they didn't bother too much. Joyle, when I talked to him, Joyle, why didn't you pursue that line of research? Ah, well, you know, we thought it would spare the tumor as well, and we had no funding. So we went on. It's exactly what we didn't do when we worked with Vincent Favaudon. We saw the sparing at the normal tissue level in the lung, as Paula showed you, what we call the flash effect. And it's to tell you that you have to do the experiment before you draw any conclusion. Yes, it might be kind of obvious, but sometimes you would be very, very surprised by the results. So until an experiment is done, you don't have the result. So do it and push that direction in order to push the boundaries and to think really outside of the box. So today we know that this flash irradiation in one but destroys the tumors. And that's why it has been defined of researchers coming from all over the world, and the main center in Europe, in the US, but also in Asia. And you see here in this picture, some people from Africa are also interested, are coming into the game. And I think it's a super, super important opportunity for all of us to make and to push this approach toward the clinic in a safe manner for many reasons. First, we will have a big increase in the number of cancer patients in the next few years, and it's going to be true everywhere, all over the world. Second, radiation therapy is one of the most important cure provider in cancer treatment, with a large number of patients that could benefit of radiation therapy. So that's another important point. And the third point is that radiation therapy can be accessible to most of us all over the world, whereas the biotherapy, look at the immunotherapy, for instance, are super expensive. Only a very small number of wealthy people are going to be able to benefit that, whereas us, with our devices, with one single machine, we can treat many patients. And if we are using FLASH, we reduce the time needed for irradiation. We reduce probably also the fractionation, the number of fractions that will be needed to treat the cancer, and we can treat more patients in the long run. So it's a complete benefit, and it has also been supported mainly by the academics. So the academic people push this field. So I will shift, and I will tell you a little bit more about what we can expect at the tumor level, because Charlie mainly spoke about what we've done at the normal tissue level, and to be honest, most of the work that has been done focused at the normal tissue level. But there is an entire field of investigation that is to try to understand how tumors are destroyed by this flash irradiation. And I will also show you that we can probably have more efficacy in certain types of tumor when we are doing an irradiating flash. And we have been investigating this question primarily in hypoxic and hyperoxic systems. And the work was done by Ron Lewitt in my lab. He took a very simple system of glioblastoma cells and grafted in the flank of mice and did some irradiation of these glioblastoma cells. So you see in black the irradiated curve. He put the animal under hyperoxia using carbogen, and then you see that irradiation sensitizes the tumors. This is pretty straightforward, classical oxygen enhancement effect. When he clamped the tumor, it was the reverse. he was able to radioprotect the tumor. So it's pretty well known. After conventional irradiation, hypoxic tumors are more resistant to conventional irradiation. One big surprise came when we flash irradiated those tumors. You see that when we clamp the tumor, we are not losing the efficacy of irradiation, meaning that we could maintain the efficacy, anti-tumor efficacy with FLASH, which is not the case with conventional dose rate irradiation. So we did several RNA-seq analysis experiments, and we showed that in normoxia, in this system, there was no major differences in between irradiation at conventional dose rate and FLASH, whereas where we are irradiating hypoxic tumor, a large number of genes were altered by FLASH only. And when we made the analysis of those genes, you can see that some were related to the cell cycle and DNA repair pathway, and some others were related to the ribosome biogenesis, showing that we have probably an hint at the cell cycle level, and we think we have identified one factor that could be very important to modify this, which is a protein called GAT45, and we have also this ribosomal imprint that is fitting very well with the metabolic switch that we've been seeing as well in this type of tumors. Then what Ron did was to modify and to alter this metabolism using an inhibitor, and here as well we've been able to push a little bit more the impact of FLASH radiation resistance. And we are investigating this using a new model developed by my colleague from the CHUV, Ganrich Tolstonok, who developed a bar-coded system which enables us to look specifically at one cell using a color code or a barcode. And when we did this experiment on those barcoded cells and investigated FLASH versus conventional irradiation, we found that FLASH was able to induce a stronger reduction of the clonal complexity. Here in that picture, you have all those dots that are the clonal constitution of those tumors. And here you have the control tumors, non-irradiated. Here you have the FLASH irradiated on the left with kind of mini clones remaining inside the residual tumor after irradiation. And here we have the FLASH irradiated tumors. And you see here that the clonal complexity is much narrow, 85% in these tumors, meaning that we're going to be able to target them afterwards with probably a biomolecule. So this is work in progress. So it's what I wanted to tell you today. I want to finish this talk by inviting you at the FRPT conference, if you have the opportunity to come over to Rome in December. And I really would like to thank my colleagues now at the University of Geneva. So you see the pictures that Paola showed you. We have a very young researcher in the team. We loved very much Fernand. And all the team in beautiful Switzerland. Lot of snow over there and a lot of mountains as well. And I'm happy to take any question.
Thank you very much, Professor Rosenan. Tenemos tiempo para dos preguntas. Two questions, please. Doctora Garcia.
How you quantify the dose deposit in your experiment? Oh, I think it is not possible to use a ionization chamber because no. Integration times, I
no,
think it's not possible.
In fact, we have developed a very systematic and redundant way of monitoring the dose during the past few years. But you're right, it was one of the first challenges in this field. So what we're doing is we are using a set of passive dosimeters. So we use GAF-chromic films, we use TLD, we use alanine, and we also have now embedded into our system some correction factor to be able to use Marcus chamber. So we can use, upon applying a correction factor, a Marcus chamber. And now what we're using more, especially when we are working with the Linacs, is coil, so ACCT coils, in order to be able to measure the dose. For the development of FLASH irradiation in the clinic, I guess that we're going to have by Marcos a talk dedicated to this question, but there is now quite a lot of dosimeters that are available, especially diamond-based dosimeters, silicon-based dosimeters. So now, I mean, when we started, 15
but the
years
diamond
ago,
don't have a dependence on the range dose?
well, those have been characterized to be dose rate
including
independent.
the radiochromic field, I think.
Yes, synthetic diamonds doesn't have.
No, they are dose rate independent. They have been validated to be dose rate independent.
And do you think it's possible or necessary to implement a new code of practice of this new technique?
I didn't get your
code
question.
of practice.
A code of practice for
Yes, a
reference
code of
dosimetry.
practice. Well, I guess it's on the way. There is the European group from ESTRO, who has launched a physics group who is working on this question of really implementing guidelines and code of practice. And the American, the APM group is also doing the same. So I guess that both those two big groups of medical physicists will come to some, I think one of them has been published over the summer already. But yeah, it's a big, I guess it's a biggest question for the translation of flash irradiation in the clinic. The second big is to have the right accelerators and to define, as your colleague said previously, what the optimal dose rate is, because that's still a big question.
Una sola pregunta.
There are some experiments that have the zeitgeist consider the mouse zeitgeist. It has any importance in your experiments with FLASH, or it has?
I didn't get the first.
There are some experimental with the mouse zeitgeist. I mean the chronological biological time. So because with the conventional radiotherapy, there is the immune response.
CGAS. Okay, sorry. Yeah, it's my bad. My
okay.
bad. Yeah. Well, yeah. We have investigated in this work this CGAS-STING and interferon pathway, comparing both conventional and flash irradiation, and we end up with the same type of activation. So for us, what is happening in the conventional does happen also in the flash, but our main question was, do we have a better immune activation after flash exposure? Which, to be honest, I was expecting, because I was telling myself, because we have this irradiation so intense, we should be able to release more antigens. And obviously, with the experiment we've done, at least in mice, it's not the case.
Okay. Thank you very much.
Muchísimas gracias. Por favor, un aplauso. Tenemos un par de avisos. Los invitamos a seguir preguntando y los invitamos a la mesa redonda que va a haber al final del simposio, donde pueden expresar todas las dudas que hayan quedado pendientes. Otro aviso, tenemos un café de 15 minutos, más o menos, aquí en la sala de usos múltiples, está al lado del auditorio, y los invitamos a visitar a los patrocinadores, que a final de cuentas pues, nos ayudaron a que este evento fuera posible, pero sobre todo en la sala de usos múltiples va a haber una plática sobre los equipos preclínicos que ofrece Explorar para radioterapia FLASH. Entonces, ahí también se va a servir el café. Entonces, como que guarden silencio, si quieren seguir platicando sobre el evento, los invitamos a que lo hagan afuera de la sala de usos múltiples. Hay un pasillo bastante amplio, solamente para que puedan ya sea escuchar la plática o dejar escuchar a los demás presentes. Bueno, nos vemos aquí dentro de 15 minutos. Muchas gracias. Pero no los voy a cortar en 15. Nadie mira el tiempo. Sachazo, ¿no? Hola.
Vamos a ver preguntas.
Gracias. Ven.
Me viene el escalón.
Aquí, a la derecha. Muy bien. Ayer en la tarde les cayó, pero en la mañana escuchando. Qué bueno, qué padre.
Test. Test, test.
Doctora, ¿nos escuchas? Sofía, ¿nos escuchas?
Can you hear me?
Yes.
Perfect. Thank you.
Thank you.
So, good morning, everyone. I hope you are enjoying the coffee break. And thank you so much for Paula for organizing this fantastic symposium and for the opportunity for us as Extra to present. My name is Sofia Talos, and I'm the North American Sales Director for Life Sciences at Extra. To give you a bit of an insight into who we are, Extra has been a global expert in radiation for over 25 years and has been shaping the development of orthovoltage radiation therapy and preclinical radiation research. Extra has two parts of the business. One is that doing medical systems that are used to treat patients in clinics throughout the world. And the other one is the life sciences section, where we manufacture just simple single-plane cabinet radiators, and also the SARP series, which is the gold standard in conformal irradiation in a preclinical world. And our most recent innovation is the FLASH irradiators that are dedicated preclinical irradiators that are capable of delivering over 100 grays per second. So why did we come up with the idea to manufacture a photon flash system? Well, here you can see a couple of the currently used systems for flash irradiation. However, these are very complex systems that are usually not initially designed for preclinical purposes. Also, they take up a lot of space and also budget, both initially and for maintenance. And they're usually located in the vault, so therefore they are not as accessible for preclinical research purposes. So then the question came up, do orthovoltage X-rays offer a simpler solution? So here you can see the SARP flash irradiator that we have developed. The SARP flash is a fully self-shielded system that provides you with 3D photon flash irradiation for preclinical research purposes in small animals and in vitro. It has a two-tube setup. Oh, you can't see the slides.
We cannot see the slides.
I can try to share again. Can you see it now? Perfect. Thank you. So I might just stay in this view because this one works. So basically now you can see the SARP flash on the system, which is a 3D photon flash irradiator for preclinical research purposes in small animals and in vitro. It has a parallel opposed tube setup to make sure that even though we are using orthovoltage X-rays, it provides you with homogeneous dose rates and flash dose rates throughout the depths of an animal. It also provides you with high translational value due to minimal penumbra and therefore being able to do more conformal dose distributions. And since it's a self-shielded system, it has a relatively small space requirement and provides you easy access for preclinical research. It also has a third X-ray tube and a CT imaging panel, so therefore it also allows you for image-guided irradiation and 3D IGRT capability. The tube itself is capable of a ramp-up time in the milliseconds, and therefore it provides you with instantaneous flash dose rates and can achieve over 100 grays per second throughout the depths of a mouse. So why would you basically choose a photon flash irradiator? Well, I've already mentioned that it has a minimal space requirement compared to other options and can provide you easy access for preclinical research purposes. You also don't have to basically compete with the time with patients to be able to access the irradiator. Other than that, it is very easy to use and has advanced capabilities that you might not have on other irradiators for flash purposes, such as the image guidance capability. It also allows you with accurate targeting and collimation to millimeter scale, so you can actually do suborgan irradiation in small animals as well, and that is also due to the minimal penumbra that is associated with orthovoltage X-rays, and therefore your dose distributions will be more translational and clinically relevant. When it comes to the use case scenarios, basically, as I mentioned, it is designed for preclinical research purposes, so you can use it for in vivo irradiation in small animals, such as in mice, as you can see it on the left side of the slide, and also for in vitro irradiation, so for example for cell plates, as you can see it on the right side of the slides. We have two options for the flash systems. One is the SARP flash. So basically, this is what I've showed you previously about the minimal penumbra. And here are the use case scenarios, so the in vivo irradiation and the in vitro irradiation for cell plates. The tubes have vertical separation, and therefore, by changing the MA and the SSD, you can actually alter the dose rate, and therefore the system is capable of both flash and conventional dose rates. By modulating the MA, you can actually do flash and conventional comparative studies, and it is also capable of SFRTs due to the very high dose rates. By opting for the SARP flash, you also get the targeting capability and conformal dose delivery, and the potential for pencil beam scanning. So basically, all the advanced research areas that we are currently looking at, you can do this with this irradiator. Now, although photon flash is a new innovation, and a number of high-level physics and biology journal articles have already been published using the extra flash systems. First of all, there are physics publications that have been looking at the dosimetry and the characterization of the system. And there are also biology publications looking at in vitro models and also in vivo models and looking at the flash effect in mice. There are some ongoing experiments looking at tumor control, skin, eye, pancreas, and brain responses, and some future studies that are planned around SFRT and mini-beam pencil beam scanning as well. So here you can see one of the examples of the biology publications that's already out there looking at skin toxicity. So this was done at Johns Hopkins University, and they were looking at skin toxicity with flash versus conventional irradiation. And as you can see on the images, they have delivered 35 grays and 43 grays with flash or conventional, only modulating the MA on the system. And they scored the skin toxicity levels, and they have also looked at the histology, and they found that there was significant flash sparing effect in both of the FLASH groups compared to the conventional irradiation. Now, skin has been a heavily studied area when it comes to flash sparing, but they have also looked at eye sparing effect. So they were looking at conventional versus flash irradiation with 22 or 35 grays, and they were looking at whether or not the eyesight of the animal was spared. Basically, as you can see on the graphs, at 22 grays, the eyesight was actually spared in the flash group, while in the conventional group it was lost. Interestingly, at 35 grays, both groups lost the eyesight, which basically meant that there is a window of threshold for the dose delivered in which the flash sparing effect can be seen versus not seen. So it would be interesting to further study this and identify this window of opportunity tissue specifically. Now we have looked at the healthy tissue sparing effect, and we have shown it with the external systems both on the skin and on the eyesight. However, as mentioned before at the talks, tumor control is just as important when it comes to using FLASH. And this is what this publication was looking at. So basically, animals were irradiated with 35 rays, conventional versus FLASH. As you would expect, in the untreated control group, the tumor growth continued rapidly. However, in both the FLASH and the conventional groups showed comparable tumor control, showing that these FLASH irradiators are capable of comparable tumor control as conventional irradiation. Last but not least, if you're interested in basically getting a dedicated preclinical irradiator for your FLASH research, you are not only getting a system, but you are also getting a support system for you. We do believe that groundbreaking discoveries are achieved through collaboration, and we foster collaboration between users and us, and also between users themselves. So as you can see, we have annual symposiums and also a dedicated FLASH consortium to drive this technology further. So we would very much love to welcome you and see you contribute to this field. So basically, as a quick summary, if you are interested in the extra photon FLASH irradiators, please note that this is the only FLASH irradiator with IGRT potential, and that is specifically designed for preclinical research. We have exceptional billet quality and targeting accuracy, and due to the minimal penumbra that's associated with orthovoltage X-rays, it is supporting conformal dose delivery and improved translational value of your research. It is also space efficient and accessible and easy to use for researchers. And last but not least, we have an established and growing user community with opportunities to collaborate. And please see a quick video just as a summary. And thank you very much for your attention. I hope you are still enjoying your coffee break. If you would like to download the brochure of our FLASH systems, please use this QR code. And if you're interested in getting more information or booking a meeting with me, then please do so. My contact details are here, and you can also scan this QR code on the right to access my contact details. In addition, my colleague Fatima is also present in person at the conference and would happy to provide you with more information and contact details as well. Thank you very much.